In our last session, we have discussed about the other data structures like the linear data structures, the arrays, the linked lists, and the others. So, in this particular session, we will be discussing about stacks and queues. So, what are those data structures we will discuss? So, uh, in, uh, in our discussion, we will just discuss about stacks, what stacks are, and how we can implement, and for what purpose we can use a stack. Similarly, we'll have discussion on queues, what are queues, how we can implement queues and the types of queues, and finally we will have some application areas or some examples or some scenarios in which we can use queuing. So a stack is a simple data structure in which insertion and deletion occur at the same end. So here, this data structure, we can visualize a stack as a container having an opening from the top, and it is the only opening through which we can add items or put items into the container. So the only two operations associated with the stacks are the push and the pop operations. So the insert operation in the context of the stacks we call the push, and the insert delete operation is termed as pop. So those are the two only operations that can be applied on the stacks, and the way those two operations are applied on the stack is termed as LIFO, or abbreviated as LIFO, and this means last in first out. So in this way, in this principle, the two operations are applied. So what does it mean? The last in first out principle means when we are inserting data into the stack, if it is the first element, it will be placed at the bottom of the stack, and the others, the next items that will be added into the stack will be pushed or will be put on top of the previously added items. So the item that is lastly pushed on top of the stack will be at the top. The item that is pushed at the end will be at the top of the stack, and the item that was added first will be at the bottom of the stack. So when we are removing or popping an item from the stack, the first item that will be removed from the stack will be the one that was added at the last. That is the last in, then first out. So the item that is lastly added on the top of the stack will be removed from the stack first, and the item that is added first will be removed at the last. That's why this principle is abbreviated as last in first out, because here in this container there is no any other openings through which we can remove the added items, so that we cannot remove an item from the middle. So for the removal and for the addition of items, we use only the top opening, only the top opening. That's why we can visualize the stack as a container which is vertically oriented and having an opening from the top only. So how we can implement or bring this concept to the programming perspective, so that we can implement the concept in a computer system. So we can consider a stack as simple array, list of items. So in array, for example, if we have an array of those size, those size of six slots. So we can just consider the array as a vertically oriented container in which each slot will hold the items or the data items that are to be added on top of the stack. So for example, for this one, we first added 6, and this is the bottom, and next we added 3, the next is 1 and 4. So the last item that is added will be the top of the stack, and the bottom of the stack is 6. So this is how we can apply the push operation. So again, if we push number 8, this will be incrementing the top variable. So the top variable, after the addition of 8 on top of the stack, will increment the value of the top of the stack variable. So currently, after the pushing of element 8 on top of the stack, the top of the stack variable will point to the topmost element, which is 8. And if we apply pop operation, that is removing an element, so since it is the application of the pop operation will obviously remove the topmost element, it will not receive any parameter that is an element to be removed, but because it is already known that the topmost element will be removed. So the application of pop operation will remove element 8 from the top of the stack. Then the top of the stack variable will be moved down one step, so pointing at element 4. So those are the only two operations that we can apply. So here the push operation takes the an item as a parameter, an item to be added on top of the stack as a parameter, and the pop operation here doesn't receive any parameter, because it is known that the topmost element will be removed. Instead, it will return the element that is removed from the top of the stack, and the push operation will not return any value, rather it will receive an element to be pushed on top of the stack, So here our purpose is to develop the stack implementation that doesn't tie us to particular data type or particular implementation. So we can implement this stack concept either using array concept or using linked list. So we want that set of operations that will work with either type of implementation. So the operations that will be applied on the stack will be implemented in either of the implementation types that we selected. So if we selected an array as one way of implementing the stack, so we'll define those two operations, the push and pop operations, to work on the array. If we applied or selected the linked list as another way of implementing a stack, then we will define push and pop operations in terms of the addition of a node into the list as push operation, and the removal of a node from the stack or from the linked list as the pop operation. So when we are implementing the stack using array, so the array implementation of stack, so how we can implement the push operation, so as we have said, this push operation is the operation of adding an element on top of the stack. So the addition of an element in the context of a stack, we call it push operation. So if an array is given to you which is supposed to act as a stack, so here we are considering array to be considered as a stack. So you know that it has to be a static stack. That means, so the data overflow if you cross the upper limit of the array. So we have to keep in mind this this condition. So if the maximum limit of the array is reached, so the overflow condition will happen. So we should check whether the stack is in the overflow condition or not, or in the overflow state or not. So when we are pushing an item on top of the stack, first this simple algorithm summarizes the push operation. So in the step 1, we first increment the top variable by 1, which is indicating the slot in which we can add the element to be added on top of the stack. So we should check whether it is always less than the upper limit, because the upper limit is very important for checking if the stack is in the stack and overflow state or not. So if the upper limit is less than the top is less than the upper limit. If the top is less than the upper limit, then that means there is a space into which we can push the element that we want to add on top of the stack. If not, that is, the stack is in a stack overflow state. So that is the condition that we should check. So upper limit is just the maximum size of the array, that is the number of elements, the maximum number of elements that can be stored in the array. So we should check if the top variable, because here the top variable is used as an index, and indicating the location or the slot into which we can add an element on top of the stack. So those are the two steps that we can consider. So the simple implementation, when we are converting or implementing this push algorithm, the push operation algorithm, here we can just use, or we can declare stack as an array. So this is a declaration, the declaration of the array as in static. So this is array, or the stack declaration, the array, indicating the stack, or representing the stack. And here the top is initialized with -1 to indicate that currently the stack is empty. So when we start pushing an item on top of the stack, as per the steps of the push operation algorithm, the top, we should first increment the top variable by 1, so that we can let the top variable to locate the first slot of the array. So initially the top variable is assigned the value -1, so -1 plus 1 will be 0. So when the top is equal to 0, that means the top is representing the first slot of the array. So now, before putting the element on top of the stack, first we should check if the top is less than the upper limit. So we just assume that the upper limit is just declared somewhere in the code and assigned the maximum limit of the array. So if the top is less than the maximum limit, that means there is a space into which we can add the item that is received by the push operation. So the stack of top equal item, simple. Then if this condition is false, that means the stack is overflow. The stack is in overflow state. So that means there is no space in which we can add the received item. So in that way we can implement the push operation. So in push operation we can receive an item that is to be added on top of the stack. So what about the pop operation? How we can implement the pop operation? So the pop operation, as we have already said, that this pop operation is a synonym for delete operation. So in the context of a stack, we just use the terminology pop for delete operation. So here the stack underflow condition or underflow state can be observed in the case of pop operation. So stack underflow means there is no any item that can be removed from the stack. So the stack is empty. That means, in other words, the stack is empty. So there is no need to apply the pop operation, or if we apply the pop operation, the stack underflow state will happen. Just like in the push operation, there is stack overflow. Here in pop operation, stack underflow is also detected if the stack is empty. So when we are implementing, we are applying this pop operation, we should check if the stack is empty or not. If it is empty, then we should report stack underflow. If not, that means there is an element that can be removed from the stack. So in step 2, we should just take the element from the array that is pointed by the top variable, because that element will be returned to the caller function. So we should take that element from the array first, and then put null value into that slot, and then decrement the top variable by 1, variable by 1. As you can see here, when we are popping, applying the pop operation, for example, the pop, after pop operation, the an element array will be removed from the top of the stack, and the top of the stack now should be reduced by 1 to point element 4. So that is what we should do in pop operation. So how we can implement the pop operation algorithm. So the implementation of the pop operation, just similarly, we can put the maximum limit of the stack, and the top variable is initialized by -1. And here, this is the pop operation calling statement. This is the calling statement of the pop operation. So this is the calling statement. So the pop operation is called, and the value that is returned from the pop operation will be the element that is removed from the top of the stack. And here what we are doing is we are assigning the removed element on a given variable. We specified the variable as popped val, and so this variable will hold the value that is removed from the top of the stack. So the pop operation doesn't receive any parameter or any argument here, but it can return a value that is removed from the stack. So that operation, how we can define that operation, or based on the given algorithm, is we should declare a variable that will hold the value that will be removed from the top of the stack. So int del val equal 0 means just we are declaring a variable that will hold the value that will be removed from the top of the stack. So the first step is checking if the stack is underflow or not. How we can do that? We can check the value of top, whether it is equal to -1 or not. So if the top variable value is equal to -1, that means there is no any value inside the array. The stack is empty. So we should report the stack underflow message. So underflow, the stack is in the state of stack underflow. If not, that means there is an element, at least one element inside the array. So we can now first assign the value that will be popped from the top of the stack on del value. So stack top will assign the value that will be removed on del value, on del variable. Then now we can, once we just took that variable value and assign on the del value, now we can place that slot, we can fill that slot by null value. This is a keyword in C++ to indicate an empty value or null value. So after the slot pointed by top variable is set to null value, now the currently element that is on top of the stack will be pointed by the top variable by reducing the top variable by 1. We should reduce the top variable by 1 to let the top variable move down one step. So and finally we should return that variable. So this is how we can implement the pop operation, So this is the implementation of the stack using linked list. And when we are implementing stack using linked list, then a very important point that we have to keep in mind is the difference between array and linked list. In the case of array, we should just think of the maximum size of the array, maximum size, because we should fix the maximum size in advance before starting storing elements inside an array. But this is not the case in linked list. So for the implementation of a stack from the types of linked lists, we use singly linked list, because in singly linked list we can move forward only. And here another thing is we should also limit the number of operations that can be applied on the linked list that is used for the implementation of a stack, because we know that a stack is associated with only two operations. So here we should restrict the other operations other than adding an element at the end and removing an element from the end. So the other operations should be restricted, so there is no need to implement other operations like removing an element from the middle, somewhere from the middle of the list, or there is no need to implement an operation that can remove an element from the start, because in the case of a stack there is no need to, or it is impossible to remove an element from the bottom. If we implemented that operation that can remove an element from the bottom of, from the start of the linked list, that means we haven't implemented the stack as linked list. So our linked list will be the regular linked list, but not the one that is implementing the stack concept. So we should limit the two operations only. Application of the implementation of the two operations on the single linked list. So the push operation, how we can implement the push operation if we are implementing the stack as a linked list. So the simple algorithm, the first step is we should check whether the stack is empty. So if the stack is empty, we go to step 2, or if not, we go to step 3. So create a new element. Step 2, we should create a new element and make that stack and top pointer variables. Here when we are implementing the stack in the form of linked list, as you can recall, the linked list can be implemented with the help of the structure concept, self-referential structure concept, and the pointer concept. So here we'll be utilizing the pointer concept and self-referential structure concept for the implementation of the stack using singly linked list. That's why here the stack is considered as a pointer and top variable is also considered as a pointer. So in step 2 we should create the new element and we should make the stack and top pointers to point to that new element and store. If not, if the stack is not empty, then we should create a new element and make that the last or the topmost element of the stack to point to that new element, and we make in the last step we make the new element the topmost element by making the top element to point to it. So this is the simple starting point of the implementation of the stack. So here struct node, then item, this is the data part, and this one is the pointer part, which is creating or making the link between the nodes of the linked list. So initially we should make the stack the null value, that is initially the stack is empty, and the top pointer variable, which is of type node, is also pointing to the stack. So initially both are pointing to the null value. So here when we are implementing this algorithm of the push operation, so the push operation is receiving an item, the push operation is receiving an item. So if here after receiving an item, here this is a calling statement, this is a calling statement of the push operation. So after this function is called, then we pass an item. Here this is an item or any value that will be assigned to the data part of the node structure, the node variable. So here after receiving the item, we should check the step 1, we should check if the stack is null, that is if it is empty. So if it is empty, that means the item, that node or the new node that will hold the item value will be the first node in the chain. So we assign, we declare the new node, we declare the new node, we create a new node and assign the value of the node by the value which is passed to the push operation. So here an item which is assigned to the data part of the node pointer, new node pointer, and the pointer, this new node next pointer will be set to null, value. Why? Because it is the first node that is at the bottom of the stack, So as it is the first node of the chain or of the stack is equal to the new node, and top is equal to stack. So here the top is pointing to the first element of the stack or the first node of the stack, and the stack is now containing that new node as it is first node of the chain. If the stack is not empty, that means the stack is already having some nodes, one or more nodes. So we should move to the else part, and what we can do is we just take the same step here, we do the same, similar to this one, we do the same step, but here what is different is the top next The only thing that we should change is the top next is equal to the new node, because here in this part we are considering that the stack is only already having some items or some nodes. So the top most node will take the new node as it is next node, and the new node will be the topmost. That's why we are assigning the top pointer by the new node. So this is the way we can implement the push operation. And the pop operation, is just the removal of an item or the node from the top of the stack. So here, when we are implementing the pop operation, we should let the delete operation to remove an element only from the end of the list. Only from the end of the list. We should not let the other delete operation implemented on the stack that might remove an element somewhere from the middle of the list or from the bottom or from the start. So the only operation that can be applied on the linked list is the one that can remove an element from the end. So how we can let the delete operation or the pop operation implemented as an operation that can remove an element from the end of the single linked list. So here when we are implementing, the first step is we just got the target to point to the last but one node. But here we should just make the another variable that is target, another variable that is we use another pointer variable that is pointing to the last but one from the last node on the next level from the last, that is for below the topmost node. So we need to use another pointer named target pointer that should point to the a node below the topmost node. Why we are targeting that node is because after removal of the topmost element, the top variable will be moved one step down to that node to make the next node as the topmost element or the topmost node of the chain. So that's why we are using the third pointer target. So we in the case of pop operation, where when we are implementing the stack as a linked list, we should use another third pointer named target, so that we can just easily bring the top variable down to the node that is pointed by target pointer. So once we targeted the node that is below the topmost element, then we remove, in step 2 we remove the element that is on top of the stack. We remove it, then we bring the topmost element down to the node that is pointed by the target. So the target node will be used as a topmost element. So here when we are implementing the push operation, the stack underflow state is still available. Whether we are implementing the stack in the as a linked list or as an array, in both cases, cases. The push operation is associated with the stack underflow state. So the stack underflow, although the upper limit is not the concern or issue in the case of linked list, the stack underflow is still available, because stack underflow is just representing the empty. The stack is empty. So the first step is checking whether the stack is empty or not. If the stack is empty, then we should report stack underflow. If not, then either only one element in the stack. If there is only one element in the stack, then we remove that element, and then we go to next step. So if we check it that the stack is having only one element, then we should remove that element and make the stack top and bottom pointing to the null value. If not, then after the removal, we make the target. Making the target. If not, that is, if the stack is having more than one element in the list, then we should make the target to point to the element below the topmost element. So then after that, we can remove the topmost element and letting the target to be the top pointer to be moved one step down to the node which is pointed by the target. So here this is the complete implementation of the pop operation, the complete implementation of the pop operation. So here this one is the stack self-referential structure, which is representing the single linked list, because here we are declaring a single pointer that will create chain or link between the nodes. So due to the existence of only one pointer variable in the pointer part of the structure, this structure is representing a singly linked list. And here the structure in this data part only one variable, but we can also add more variables depending on the requirements of our problem domain. So depending on the problem requirements of our problem domain or the scenario that we are implementing, we may add more data variables. Or at the data part we can add more variables depending on the requirements of our problem domain that we are about to solve using the stack. So here, once we have defined the structure, then we initialize the stack and top to point to the null value. Then in the main function we can call the push and pop functions. So since here we are implementing the pop operation, now the pop operation based on the specified steps of the algorithm. So we can implement the pop operation like this. So we just initialize the variable, the value that is used to hold the value that will be removed from the stack. So the first step is checking whether the stack is empty or not. If the stack is empty, we should report the stack underflow. If not, the first is checking whether the stack is having only one element. So that means if top is equal to bottom. If the top is equal to bottom, that means the stack is having only one element. So we can take the value of that node and assign on pop val that is the value that will be returned to the caller function, and then we can delete the top most element or the topmost node, because delete operation here, the delete operator, the keyword, this is delete is the keyword, and it is possible because we are declaring, we have declared the top variable as a pointer variable, and we know that the two keywords, the delete and the new operators, are the ones we can use for dynamic memory management. So we are dynamically as dynamic memory management, we use the two operations, the new and delete, for dynamically managing the releasing or the reserving memory. So reserving a memory, dynamically reserving a memory using new operation, and dynamically removing or releasing a memory, reserved memory, using delete operation is possible. So for the dynamic memory management, we use the two operations, delete and new. That's why we are using the delete keyword for removing or releasing a node, space which is reserved by the top pointer variable. And we can set the stack to be null value, and the top, bottom and the stack all are equal, because now the stack becomes empty. Else, if the stack is not containing only one element, that means more than one elements are there. Okay, if that is the case, then what we should do is first we should move to until we reach at the node that is below the top, using this while loop statement. So while the target of next, we should start our target from the top, from the bottom. We should start moving up until we reach at the node below the top. That is why the condition is specified as different from top. So until we reach at the node which is below top, we should continue moving up to that point. Then once we reach at that point, then we should assign the value of the top node to pop val, because that value should be returned to the caller function. Then after that we can delete top. Then what adjustment we should do is the top should be equal to the target one, because here we move to the node that will be set as a new topmost element using this looping statement. Then the target of next is equal to null value. That means the new top element is pointing null value because it is set to the top of the stack. So in this way, then finally we can return the popped element to the caller function, that is to the main function. So in this way we can implement the push operation, the pop operation. So where we can use the stack concept, so we can have different applications of a stack. So for example, when we are evaluating the algebraic expressions, the mathematical expressions, for example here the mathematical expression 4 plus 5 times 5, the simple calculator will return the value 45, and the scientific calculator will return 29. Why this happens? Because the scientific calculator will consider the operator precedence. Whereas the simple calculator will simply perform the evaluation of the expression from left to right. So when it is calculating the expression from left to right, 4 plus 5 is 9, and 9 times 5 is 45. And the scientific calculator will consider the operator precedence. That is, first we should evaluate multiplication. So 5 times 5 is 25, then 4 plus 25 is 29. That is the correct solution, the correct solution of the given expression. So how internally those expressions are performed by the computers. So here, the method of evaluating arithmetic expressions is considered or performed using the stack application. Internally, computers are using a stack for the evaluation of expressions. So basically, we do have different types of expressions. So the infix expression, the postfix expression, and prefix expression. So the infix expression, the types of expressions, the infix expression is the one that is having operators between operands. So between 4 and 5 we have plus. So operator plus is an operator, and operands are 4 and 5. 5 and 5 are operands of the operator multiplication. So this is infix expression. So we humans easily understand the infix expression type. And the other is the postfix expression if the operators are after. If the operators are after the operands. So if it is after the operands, we just consider it as postfix expression. If the operators are before the operands, we call it prefix expression or prefix form. So this postfix or prefix representation of an expression, we call it Polish notation. So the infix expression is first converted into the infix expression is first converted into either postfix or prefix and then evaluated. So we have here the postfix expression. For example, for this one, for this quadratic formula, we can convert this infix expression into postfix. So just simply bringing the operands, the operators after operands. So this equal sign is lastly assigned here, or lastly specified, because it is the operator that will be evaluated at the last step. So because the evaluation of this part of the expression will be finally assigned on x. So we can just bring this assignment after all expressions, sub-expressions, and total expression of the given expression is evaluated. So after the expression, the right hand side expression is evaluated and then finally assigned on the variable x. That's why we put the assignment operator at the last. So B here, this minus is represented by at symbol, just representing the unary operator. So in order to differentiate it from the binary subtraction operator, that's why we use it at symbol. So it is applied on B, so that's why we should bring it after B. And this plus is applied after this evaluation of from this part up to this one. So we should bring this plus after this the exponent, after the exponent. So this B, the other one, the B is 2 and the exponent, because the exponent is applied on B and 2, and minus is just applied after this product, and the result of this exponential expression. So we should bring it after C, multiplication C. Then I mean the exponent, this minus, bring it after this one, and this half 0.5, and the exponential or the exponent operator then applied on this part, and 0.5. That's why we just assigned after 0.5, and this plus is applied between minus B, so and this part, so that's why we put it plus here, and 2 over is applied on this part, on this whole part, and the product of 2 times A, so we should put it after this one, and 2, then A, then star, since star is applied on 2 and A, we should bring it after A, the multiplication after A, and then before the multiplication we have the operand is 2 and A, then finally equal sign. So in postfix notation, parentheses are unnecessary and easy. This notation is easy for computers, for evaluating expressions, arithmetic expressions. So we do have an algorithm that can evaluate once an infix expression is converted into postfix. So once the postfix expression is represented, then using the algorithm which uses stack, it will be easy to evaluate. So for example, if we have such postfix expression having the numeric values, so you should consider the 6, 5, 2, 3, 8, 3 are just independent numbers. There is a space between the numbers, so those are independent numbers. So how we can implement this algorithm? So the first step of this algorithm, this postfix evaluation, this is a postfix expression that is to be evaluated by this algorithm, and this algorithm is used to evaluate this expression. So how we can evaluate it? So based on this algorithm, we first just start reading the postfix expression from left to right, so until we reach at the star, we should start reading the number 6 and pushing on top of the stack. So here what the algorithm says is, first, if the number that we have read from the postfix expression is, if the item that we read from the postfix expression is a number, then we should push on top of the stack. Assume that we have pushed it. Then we push it, this one, we push it, Next, it is 5. It is a number, so we should push it. So this is a top element. Now the top element is 5. The next is 3, I mean 2. Again we should push it. It is 2. Now it is a top element. Now the top element is 2. The next is 3. We should push it. It is 3. Now the top element is 3, not 2. The next is plus. This plus is the binary operation. So what we should do is, if it is binary operation, we should pop two numbers from the stack and assign on a variable x. So x will be assigned the value topmost element. So we should apply pop operation on the stack content currently 3, 2, 5, 6. So when we are applying the pop operation on the stack content, the first element, that is the topmost element, is 3. So x is 3. The next element is y. So we should pop the next element is 2. So here the two elements are now popped. So currently the topmost element is 5. Then what we should do is then doing the operator y operator x. Y, the operator is what? Plus. The operator is plus. So y plus x is equal to 2 plus 3, which is 5. So we should again push the result on the stack. So the result is pushed, which is 5. Now the top is 5, the new 5. The next is 8. So we should push 8. It is a number, so we simply push the number. Currently 8 is the topmost. And the next one is multiplication. It is binary, right? It is binary. Then again we should just pop the first topmost element, which is 8. Then the next element y, which is 5. So the two are now popped. So now the topmost element is 5. We should apply the operation y multiplication then x, which is equal to 40. So we should again push 40. Now it is, the top is 40. It's not 5. So that currently it is 5. 40 is the top. Again the next is plus. So as it is a binary, again we should pop x to 40, then y to 5. Then applying the operation y then plus x, which is equal to 45. Now we just popped the 2, the 6, so 45 is pushed again. So the top is 45. The next one is 3. So we should push 3. It is the top. The next item is plus. So it is binary. So we should pop x to 3. Then y to 45. As it is plus, we the result is the result of y plus x, which is equal to 48. So then we should pop. Then for 5, so for 8 is pushed. So this is the top. Next is multiplication. So again, what we should do is popping x2 for 8, then y2 6. So it is a multiplication. So y times x is equal to 48 times 6, which is 288. We popped for 8, we popped 8, so finally we have 288. So this is the final, this is the final expression, I mean the final result of the given postfix expression. This is how this algorithm evaluates the given postfix expression. So this is an application of stack, because here the algorithm is using a stack in order to evaluate. While it is evaluating the given postfix expression, it is using a stack. This is one application of a stack. And to convert infix expression into postfix, into such representation, in order to convert an expression, infix expression, into such postfix expression, another algorithm is also there that converts infix into postfix, and this is also using a stack. Is also using a stack. So based on the operator precedence, we can convert the infix into postfix. So this is an algorithm that converts infix into postfix. So let you read this algorithm, and then convert the infix any expression into postfix. So this let you consider this infix expression into postfix. So when you are converting, just you should read the postfix expression, infix expression, from left to right, and based on the steps of this algorithm, you should put the items in their appropriate location. Another application of stack is function calling. So especially for recursive function calling and recursive functions. So for recursive functions, every function calling statement, the calling statement is stored inside the stack, and read in reverse way. So internally, the computers are using the stack for evaluating the recursive function calls. So that's all about stack.